Okay, here are some box problems that I wanted to discuss. The first one is, as you can see, it's an ester, it's a lactone, and on the product side you have an open ester and there is an alcohol. So if you basically think about it, we have added, if you were to count, first of all, if you were to count the number of carbon atoms, 1, 2, 3, and 4. So starting from the ester, that's 1, 2, 3, and 4. Notice there is a methyl that we have added, and we have added an OH. So how about I start this, I treat it with methanol in presence of an acid. So the acid is going to simply, just to give you a flavor for this, of course you don't have to show your mechanistic work, but realize that it's going to activate right here. Electrons are going to move and methanol is going to then attack. And then when the electrons come back, essentially the ring will open and you're going to end up with the open form where you have the methyl ester on one side and the OH free alcohol on the other side. The second question is, you have a carboxylic acid and I'm treating that with thionyl chloride followed by methylamine. Realize thionyl chloride is a way to convert the C double bond OH into COCl. So once you have generated the COCl, the next step will be quenching with the amine. So you are going to get an amide at the end of the day. So you're going to end up with the same number of carbon atoms, but now instead of the Cl, you would have the NHMe, because HCl would have been the byproduct. The third question is, you have been given an amide, you're treating that with H2OH+, which basically means you have hydronium ion in place. So that should hydrolyze the amide into the corresponding carboxylic acid. So the first step should give you COOH, followed by treatment with thionyl chloride. So that should convert the COOH into COCl, and ultimately that you have sodium acetate. That should give you the corresponding anhydride. So on one side you will have a T-butyl group, C double bond O, oxygen, C double bond O, and the methyl. So the Cl and the Na will form sodium chloride, and the rest of it will just hang in there as an anhydride. Okay, so I have another one where I have a carboxylic acid and I'm treating that with alcohol in presence of an acid. So this is Fischer esterification essentially, where the COOH will be get converted to COOMe. And then the diol is, recall, very specific for the reduction of esters to give you an aldehyde, and the H3O plus is basically to get rid of the aluminum. So your product should be the same ring and now an aldehyde as your functionality. Let's take a look at a sequence. We have bromopropane. We are treating that with sodium cyanide and acetone. So cyanide, being a good nucleophile, is going to show a back attack via an SN2 type of a reaction to give you a CN. So it's an SN2 reaction where cyanide replaces bromine. In this case, of course, chirality doesn't matter because it's an achiral center, but if it was chiral, then R will become S, S will become R, the whole 9 yards. You know about that. When you treat this with sodium hydroxide, we are basically carrying out a hydrolysis, so this should go all the way to the carboxylic acid. Realize, I know that it's the carboxylic acid, not the amide, because I basically got rid of the nitrogen as ammonia, so that should be a pretty telling feature here. Also realize, like I said in class, cyano groups when you do this kind of methodology, cyano groups are used to increase the chain length by 1. So you started with 1, 2, and 3, and now you have 1, 2, 3, and 4. Anyway, when you treat the carboxylic acid with lithium aluminum hydride, it's going to go all the way to the alcohol. So I should have 1, 2, 3, 4, and OH. Alcohols, so I'm saying that if this alcohol is A, then 2 of those upon heating should give you an ether. Whoa. So 1, 2, 3, and 4, so it's a butyl, dibutyl ether. And Jones oxidation, that's a strong oxidizing agent that will oxidize the primary alcohol back to the carboxylic acid. That should be a product. Okay, we have propylbenzene and we want to convert it into benzoic acid. So hopefully you recall from class that you must treat this with a strong oxidizing agent such as KMnO4, followed by hydrolysis to get rid of the transition metal. That will give you benzoic acid. When you treat that with H2SO4, realize COOH is meta director. It's an electron withdrawing group, so your incoming SO3H should come in at one of the meta locations. So your structure should look like a COOH and then at meta position SO3H. Okay. Now that you subject that to bromination with FeBr3, both of these are meta directors, so your incoming Br is going to go at the only other meta position that is available, and so that's the only one sole product. You're going to end up with the structure right here. Let's take a look at another problem. We have an alkene, and I'm treating that with mercury triflate followed by ethanol, and we're then going to reduce it. Realize this is similar to the oxymercuration demercuration synthesis for the generation of the alcohols. So you're going to see, of course, as discussed in class, you first will see the three-membered ring. And now instead of water, it's the alcohol that's going to attack and ring open. So the same way, you're going to end up with oxygen and then 3 methyls to ring open that. And then the NaBH4 basically breaks that carbon-mercury bond. So this is your first product. And now I'm supposed to, notice in my products, I'm supposed to cleave the ether, and the only one method that you can do that by cleaving right here is using strong acid like HI or HBr and heating it. So it's kind of like a reflux type assembly that you have to set up. Okay, let's do another set. We have an alkene and we are subjecting that to ozonolysis. Recall, ozonolysis on the alkene is going to cleave right here at the double bond, and you're supposed to put a double bond O on either side. So your product will look like a double bond O, and the other product I have already given you. Now, if this was an alkyne, so let's say if you had something like maybe 1-butyne, that will also go through a complete cleavage, but because you have an additional double bond, it's not going to stop at the carbonyl stage. It's actually going to go all the way to the carboxylic acid. So you're going to see 2 products. One would be here, so COOH and a CO2. Okay. The next question is that we have an ether, and we are treating that with HI and heat. So recall that it's going to go through protonation first. So you will have H, and you have to ask yourself whether one of the sides contains a tertiary center or not. Because if it does, then that would rather want to form the carbocation, because that would be stable. And the I- is going to attack, so you will see an I and CH3OH as your final products. Recall also that if this was a primary or a carbon, so if we had something like so if we had something like this, where on one side you have C and then 3 H's, and the other side we have two hydrogens and 1 carbon, then the HI is still going to cleave it, but the I minus is going to approach from a direction which is less statically hindered. So it's going to attack the methyl side. So in that case, your product would be, or products would be, propanol and methyl iodide. Let's take the final run on this particular one. We have carboxylic acid. I'm treating that with PBr3. That should give you the acid halide. That acid halide, upon treatment with dimethylamine, is going to essentially generate the amide. So electrons move, come back, and then Br leaves. So you end up with N and the 2 methyls. And when we carry out the hydrolysis, it's going to cleave the amide bond, the peptide bond as we also call it sometimes. So that will give you the carboxylic acid and N-methyl and dimethylamine. And now when I just treat this carboxylic acid with another carboxylic acid, heating them together, it's going to give me the anhydride. We have talked about that in class. So this is what is going to be obtained. 1 molecule of H2O will be given off, and that'll be your product. Okay, so here I have a primary alcohol which I'm subjecting to treatment with PBr3. So recall PBr3 via an SN2 fashion basically converts the primary alcohols into and secondary alcohols into alkyl halides. So your first step here should give you a Br. Number of carbons will still remain same, so we still have 4 carbons, so that's good. And now when we treat that with the sodium cyanide, that is going to increase the chain length, and your first product should be, it should look like a CN here. And now we are going to subject that to treatment with Grignard reagent. Recall that cyanides behave much the same way as any ketone. So nitrogen is negative and the carbon is positive. So the negative phenyl is going to attack the carbon, and the magnesium is going to stick to nitrogen, and your first kind of intermediate is going to be the double bond NH with the phenyl group attached. But since we are hydrolyzing that, that's going to eventually get hydrolyzed, and your product that you should be drawing is the corresponding ketone. Like that. Now when we are subjecting that ketone to reduction conditions, it should give you a secondary alcohol because it's a ketone. Had it been an aldehyde, that would have given you a primary alcohol. And of course, tertiary alcohols cannot be generated this way. The redox doesn't work in that case. Anyway, we are now treating the secondary alcohol with POCl3, which recall is a dehydrating agent. That means it removes water. So your first step should yield a more stable Zaitsev's product like this. And then MCPBA is going to build the epoxide. So I'm going to show the epoxide with the good stereochemistry. And now when you treat that with hydronium ion, it's going to give you an OH on one side and an OH on the other side. And that's your final product. That's about it. Alright, so I have another one here where I have a carbonyl compound. So I have a ketone which is being treated with an alide. An alide, recall, you can even write that as PH3, P with a positive charge, and then CH2 with a negative charge. So that makes this a Wittig reaction. And so your product first, upon that treatment, upon that reaction, should give you the double bond CH2. So essentially, whatever is in this part past the phosphonium, that is what gets added to the double bond. And now when we treat that with HBr peroxide, that follows anti-Markovnikov's rule. So you're going to end up with the addition of the HBr, but now hydrogen is not going to go on the terminal CH2, it's the bromine that's going to go on the terminal CH2. So the rich are not going to get richer. That's what we learned in Markovnikov rule in Organic 1. Whenever we have the presence of peroxide, those of you who have been practicing the reaction rules would have seen that the presence of peroxide gives you the anti-Markovnikov rule. So now that we have an alkyl halide, presence of magnesium, that should give you the corresponding Grignard reagent. And when you bubble CO2 through that, that will give you the corresponding carboxylic acid, COOH. Thionyl chloride is going to give you the corresponding acid chloride, and then quenching it with ammonia is going to give you an H2. So that's the final product here. Treatment with thionyl chloride, again, recall that amides, upon treatment with thionyl chloride, it's a pretty strong reagent to remove water. So that's going to give you first, this is the carbon. So here's the carbon that's going to lose the water, and you will get cyanide. We are going to reduce the triple bond of the cyanide using LiAlH4. So you should get an amine. And that amine, upon treatment with the acid chloride, should give you an amide, PHCH2, C double bond O, NH. And then we have CH2, CH2, that's your molecule. And your final treatment with lithium aluminum hydride, which is also a very strong reducing agent, should reduce that amide into the corresponding amine. So we have actually used a boatload of reactions that we learned throughout the course through this sequence. Okay, let's finish this thing with one or two prepare questions. I have an ester. I'm supposed to convert it into an aldehyde, and there's some increased substitution. As you can see, there's an ethyl group, there's a methyl group. So how would you go about it? Realize that this part right now, which is where I need my substitution, it's pretty greasy. It's pretty alkane-like. Like I've said, you're not going to just use this compound with ethane and dream about putting in your ethyl group just like that. Doesn't work that way. So the best strategy would be, well, what if you are able to somehow create a double bond in between the two positions. And so one way to do that is use bromine acetic acid such that the alpha position gets brominated, and treat that with KOH. I would keep ethanol so that it transesterifies even if there's hydrolysis that goes on. So that's what I would use for the solvent. Otherwise the ester will go through hydrolysis for that step. You have the double bond. And now you have to put in a methyl group at position 4 and an ethyl group at position 3. So how would we do that? First, treat it, since it's the methyl group 1, 2, 3, and 4. It's the methyl group at position 4, so I'm going to treat that with lithium cuprate, which contains dimethyl lithium cuprate, okay? And follow it with hydrolysis. So that's going to give me a methyl and then we are going to treat it with LDA, because LDA removes alpha hydrogen, so it will generate a negative charge right here, and treat that with methyl iodide. You're going to see one format. We did several in Wiki. I did couple on the review, and I'm again discussing one, so please be ready. Alright, so we are given essentially this problem. We have to provide the mechanism. We are given an ester, and we have to put in somehow, some other substitution pattern. LDA, recall, is lithium diisopropyl amide, so I've drawn the structure of that. So it's basically a good strong base, and its job is to carry out alpha deprotonation. So it's removing the protons. So you're generating the enolate. So your first step is basically the generation of the enolate, which by the way is resonance stabilized. Hopefully you can see that. A double bond like that, oxygen with negative charge, O and ET. And the next step is that we are putting in a ketone. So electrons come back, electrons will attack, negative charge on oxygen. It's going to look like an O with a negative. We have a new bond. Maybe I'll change the color so you can see. This is the new bond. And the donor is my ester. And it was the alpha position that attacked. So a methyl on that. And a COOET is still there. So this negative charge, since we have hydronium, this negative charge is going to get protonated pretty quickly. So you'll first get the aldol. And of course, since we are heating that, COOET, since we are heating that, we have acid that's going to go through another round of protonation so that it gets protected. And let me make room here. OH2 with a positive charge, COOET. This is the beta hydrogen that's going to go now. So this will leave, proton will be lost, and the proton is lost to water. Because we have acidic system. So when we heat it, the molecule of water is lost, and what you get is essentially your product. Okay, I think this is it. Practice everything else, and I'll see you in class.